we have here in chapter exercise 6. Let's go. A particle of mass m experiences a force that varies with time as shown. If the particle is at rest at t equal to 0, its velocity at t equal to 2t will be. So at this time, what's the velocity? It starts at 0. Okay, this is the force versus time graph. Okay, fine. It's just the momentum, right? So the momentum is what? Half times 2t times f naught, right? Which is just f naught t. So that's f naught t upon m. That's our velocity. Yeah, because mass m. So b. Oh God, what is this thing? Yeah, so like B should be the thing. Okay, next question. Displacement of particle of mass 2m moving in straight line varies with time as is equal to 2 dq plus 2. Okay, displacement varies as this thing. Impulse of the force acting on the particle over time interval between t equal to 0 and t equal to 1 second will be. What? Sorry, impulse of the force acting on the particle over a time interval between t equal to 0 and t equal to 1 second. Just yeah, whatever. Just the change in velocity, yeah, all that stuff. So mass 2 versus change in velocity. Velocity is just given by the derivative, which is um, 6t squared. So change in that, it's like from 0 to 1, it's just 6. So 6 times of 2 is just 12 Newton seconds. So B should be the thing. Next question. Particle of mass m made to move uniform speed v along perimeter of regular polygon 2 and sides. Okay. The magnet of impulse applied at each corner of the polygon is, huh? Oh, okay, it changes its direction, right? So you want the magnet of impulse. Got it. Got it. So what do you have? Right. Just think about it. So initially it's just that, yeah, this is one of the sides. It's like one of these guys triangle. So this is the triangle that you are talking about. And you are at the corner, right? So at the corner, how does that change? It's like this. So initially it was going with this velocity, now it's going with this velocity. So you want to change in this velocity. Actually, I should probably write it differently. So yeah, this thing. Well, you know what this angle is. You know what? Instead of writing too small and everywhere, I'm gonna write capital N side. So then this angle will just be pi upon capital N, and this angle is the same, just pi upon capital N. Yeah, just have this velocity over there, this velocity over here. So as you can see that this component of velocity that did actually change. All that change is just this component. So what's this angle, by the way? I mean, this is, let's call this theta. This is 90 degree. This is 90 theta. This thing is with theta as well, because they're just perpendicular to this guy, right? Wait a second. It was moving along which side, by the way? It was moving along. Oh shit, that's not gonna work, is it? Wait, okay, no. This is the side, right? This is the side. Okay. It's like this. So why perpendicular? Wait, that doesn't make sense. Perpendicular though. Why that particularly? Oh, because the midpoint. Okay, that explains it. So this is our center. Drop a perpendicular from there. Wherever it hits the midpoint, that's when you have this half angle, right? So that's why this angle. I got it. So yes, this really is just theta, which means like cosine pi upon n. So yeah, call this velocity v, then you just have v cosine of theta, and then it's like v sine of theta. So the v cosine of theta part didn't actually change, but then v sine theta did change. It's 2v sine theta. So 2v sine of pi upon capital N, or pi upon 2 small n, if you really want. Right, so that's the change in velocity. We want mass applied, and then, yeah, that's the thing. This is our momentum. When change in momentum, that's our impulse, right? Yeah, just 2mv sine of pi upon 2n. So A is correct. Next question. Next, we have bullet of mass m moving with velocity u passes through a wooden block of mass capital M, which is n times small m. The block is resting on a smooth horizontal floor. After passing through the block, the velocity of the bullet is v. So it like passes through it. Fine. Its velocity related to the block is, so first of all, it's smooth horizontal floor, so there's no x component of force. After passing through the block, the velocity of let's just see. Its velocity related to the block is, no big deal. So the momentum change. Okay, let's try to think. With respect to the block, it's kind of a weird thing. Uh, right. So what's the velocity of the block though? Just have mu is equal to, or you just do the momentum change thing. So just, yeah, just v minus u times m in that direction. So what you should have is like, the velocity would just be this upon of capital M, of course, yeah, but in negative. So this is the velocity of our capital M guy. It's just u minus v upon n, and of course in the left direction. Now just have v minus of this guy. Well, that would be the relative velocity. So just get what? nv plus 1 is just n plus 1 v minus u upon n. That's the thing. Which is A. Next question. Next we have, next we have two particles projected horizontally towards each other as shown. Fine. Collide in air stuck to each other. This is from A, where the combined mass finally lands this. Okay, the velocity is given, I think. Right, this is 5 meter per second. This thing is 10 meter per second. Hey, this is kind of, they just didn't take the care to put it over here, didn't they? They should have put it right up on this arrow, whatever. So we are assuming that 2 meter per second. So this guy actually moves with 5 meter per second, and this guy moves with 10 meter per second. They collide in air and stick to each other. Okay, this is from A, where the combined mass finally lands. Oh, right. Well, think about it. You could always do the x component or xy plane thing as the combined body, right? So initially, the center of mass has velocity what? It just has zero velocity. Oh, that's awesome. So it's zero velocity. Where is the center of mass, by the way? Just 2:1 ratio. So it's just over there, right? Exactly. Yeah. Wait, is that 5 or what? This is, this really is 5. So it's 2:1 ratio. It's just not fall down. Its x velocity just vanishes. It just falls down straight. So yeah, this is what 60 meter divided by 3 is 20, and you got 2 of this, like 40 meters from A. Right, so A is right. Next question. Block of mass M pushed towards a movable wedge of 2m and height h with velocity u. Pushed up. Okay. Minimum value of u for which the block will reach to the top of the wedge is. Let's just move over there. Energy conservation most likely. Not exactly the strict minimum, but then fine. It has to be at least that. Right. Okay. So yeah, let's do this thing. What do you have? The combined momentum. Well, okay, the x momentum stuff. And when it's on the top, its xy velocity with respect to this guy must be 0, right? Because yeah, if it's not 0, then it's like still going to move in the xy direction, and then it's not on the top, right? Okay, its y direction velocity is also actually 0 because it is on the top, which means they are like moving with the same velocity throughout. Okay, cool. So all that matters, right? It could be that that velocity is just 0. Who knows? It could be. Oh, who am I kidding? That won't be happening. The x component velocity does not actually change, right? So it will just be that momentum is just small m times u. Well, this is mass m, right? Okay, so just small m times u. So you got t square upon 2m for that final state, right? The final state is just having what? M squared u squared upon 2 times the combined mass, which is 3m, and this is equal to, so initially, or just say p square upon 2m, who cares, right? Yeah, whatever. Yeah, I mean, that's the momentum, right? It's momentum in the x direction. That's still the same thing. Okay, whatever. And then this is equal to, so initially just half mu squared. But then finally you also have gravity. So there's like potential energy because of that as well. So just have plus mgh. I think this is what the point is h. Yeah, that should be the thing. So let's see what this turns out to be. Just have 6 over there. And this is like mu squared plus mg squared. That m cancels. So u squared upon 6 plus gh is equal to u squared upon 2. So just get gh is equal to u squared as 1 upon 2 is 1 upon 6, which is just 1 upon 3, I believe. Yeah, right. Just 1 upon 3. So what do you get? You just get h is equal to u squared upon 3g. So it should be at least that much. Oh, we just want what u should be. Then u squared equal to 3hg, the square root of that. So b looks about right. Yeah, b should be the thing. I mean, it definitely has to be more than that, but it could be that it's even, yeah, the lower bar is even higher. So it could be square root of 6gh or whatever it could be. Anyway, next question. Two blocks connected to an ideal spring placed on a smooth surface. Initially, spring is at natural length. Blocks are projected as shown. Okay, fine. The maximum extension in the spring will be, once again, energy conservation. So when the extension is maximum, what should be happening is that they should be moving with the same velocity, because the extension is maximum. That's what it actually means. Yeah. So we can kind of think of, right, think of like this thing. So you have x1, x2 as the coordinates of these guys, then x2 minus x1, that's the distance between these guys, or you could just say the extension, whatever. So this distance has to be maximum or minimum. That just means like the derivative of this thing with respect to something, in this case time, that has to be 0, right? Exactly. Which means v2 minus v1 should be 0. So whenever they have the same velocity, well, that's when the maximum is either minimum or maximum. Yeah. So what do you want? Ideal spring placed on a smooth surface. Initial spring is natural length. Blocks projected as just energy conservation. We know this one. It's pretty common. So it's what do you have? Just half m1 v1 m1 u1 squared plus half m2 u2 squared is equal to it's like half kx squared plus p square upon, you know what, just take a half out everywhere because it doesn't really affect anything. And now p square upon 2m, instead of that you say p square upon it. Well, p is just m1 u1 plus m2 u2, right? Yeah, that's squared because in the end they're just gonna have the same velocity, right? So momentum conservation in the xy direction. So just this thing upon the combined mass, which is just m1 plus m2. This should be our equation. They didn't actually give us anything. They gave us k. They also gave us these values. Just want what x should be. That's it. That's actually really easy. Let's calculate. So masses are 3 and 6. Okay, it's interesting. Or u, okay, just 1 and 2 are there. We'll just calculate this thing. What do you have? 3 times of 1 squared is 3. Plus this guy is just 4, so 24 is equal to k, which for now I'll just say kx squared, plus this thing. So the combined momentum, well, this is actually negative direction, so yeah, it's just 12 minus 3 is just 9 squared upon m1 plus m2, which is also just 9, so it happens to be 9 itself. So what do you get? Just get kx squared is equal to 18. And what's k? Just 200, so like x squared is equal to 9 upon 100. Yeah, another thing. Just 3 upon 10. So meters, by the way. That should be 30 centimeters. So A is correct. Next question. Remember, everything was in SI units, so that's why it's correct to do. Then SI units is 3 upon 10. Okay. L-shaped tube, uniform cross-section area A carries fluid. Oh, this thing. The force required to keep the tube in equilibrium. So think of the individual fluid particles. They have to change their velocity in average kind of way. A very weird average if you ask me, because yeah, whatever. So on average, the fluid has to change its direction from going in this way to now going in that way. So that needs a momentum. And how, sorry, that needs a change in momentum. And what provides that change in momentum, you will ask? It's the pipe itself. Normal force that this pipe puts on the fluid that causes it to change the momentum, and that normal force is usually countered by the things that attach to this pipe. Like you might have a left portion of this tube that could put up another force on this thing, and yeah, that happens. Or you could be putting force on it by yourself, like physically, if that makes sense. Whatever, right? Let's just do this. So you want the force required to keep the tube in minimum. So how does the, right, okay, first of all, you just need a force in the vector value, and then we'll do the thing. Yeah, let's just do the thing. What do you have? Each second, you just have dm amount of mass changing its velocity. So that needs the momentum of what? Dm times delta v vector, right? And that happens every dt second. So the force required is just this thing upon t. But what's dm upon dt? Just the mass flow rate, which is also just the density times the volume flow rate, which happens to be area times dx upon v, basically. So rho av times delta v vector. That's the force required. Now, this has magnitude of v squared of 2, so the force has magnitude of rho av squared square root of 2. Nice. Neglect friction, of course. So rho a, okay, what's a? Cross-section area A. So instead of having capital A, we're using small a. Okay, rho a v squared square root of 2. Yes, so a is the thing. Next question. Next, you have answered the following questions. Can a body have energy without having linear momentum? Yes, it can. It can have angular momentum. So no big deal. Can a body have linear momentum without having energy? That's a weird thing. No, it can't, because if it has linear momentum, it does have kinetic energy. Wait, what do you mean by energy? Like, which kind of energy, or like total energy would, I mean, it can be zero. Your energy can be zero. For example, you have parabolic orbits in gravitation that has zero energy. But then, this is weird. But is this correct to say that gravitational potential energy is also a part of what they are considering? I don't know. But yeah, probably you can have momentum without having energy or having zero energy. Does that make sense? You can also have negative energy, which is, I think they are talking about kinetic energy, but then it's just weird. Can a body have kinetic energy without having? Oh, okay, fine. They did have this being the general statement. So yeah, B, it is correct. You can have linear moment. You can actually have linear momentum without having energy, or like without having positive energy. Even in zero energy, you can do that. Can a body have a kinetic energy without having? Of course, it can have. Oh, in that case, A also has like a multiple different ways. Okay, it's like the potential energy as well. Can a body have linear momentum without having kinetic? Right. So D is the one that has the answer as no. All right. Next question. Bullet of mass 10 gram traveling horizontally velocity something strikes a block of wood of mass something. Okay, this guy's mass 10. This velocity is this thing. Okay, which rest on a rough horizontal floor after impact the block and okay move together come to rest on the block is the distance of this thing. Right. Okay, got it. So initially on impact, the friction is not impulsive because it is limited, right? It's limited by mu times normal force, and the normal force is actually just mg throughout. So, nice. Which means that the friction force is not impulsive, so you can just do momentum conservation. Although that's not technically in the yes, like you are not technically having zero force in xy direction, but you can still do it because the force is not impulsive, so it does not actually contribute any momentum in the end. Friction is not impulsive, right? For this case, there will be cases where friction will be impulsive. Like think about two particles colliding and then one of them is rotating as well. So like this contact point is rotate. Yeah, that surface is having friction, but then the normal force is impulsive, so the friction is also impulsive. That makes sense. I think it should. Anyway, what were we doing? Yeah, we'll talk about this thing. Bullet of mass 10 gram traveling horizontal velocity. This thing strikes a block of wood of mass something, rests on horse. Yeah, whatever. After impact, the block, the momentum move together. Okay. So the energy is just p square upon 2m. The mass is this thing of the bullet, and the velocity is that like 3000 is our momentum. So just 9 times 10 power 6, that's p squared upon 2m. So 2 times, what's the mass by the way? The new mass is just 300. So just 10 power. Nice. And this energy is completely lost due to friction. So due to friction, what's the work done by the friction? Okay, how much is this displacement, right? Okay, yeah, the friction force will just be as normal force, like mu times of 300. That's our mass, right? Yeah, so gravity is 10, assuming that. Right, I mean, okay, that we already assumed, so no need for that. Okay, so just that's our friction force, that's our displacement. And displacement is of 15 meters in assignments. Good, nice. So this is the thing. Oh god, what happened? Just wait a second. 45 mu times 10 power 3. That's nice. Okay, so now you can get mu in that way. What do you have? That cancels. Just that is 10 power 4. That cancels, just becomes 10. So what we have, just have 15 is equal to 45, mu equal to 1 upon 3, of course. Right, so C is correct in that case. Next question. Honestly, just a lot of calculation. It doesn't have anything worth teaching. Yeah. I mean, anybody could understand this if they read this actually. Right. Where were we? Okay, 10th done, 11th. Wait, didn't actually. Okay, that's the another of these guys. 20-gram bullet pierces through a plate of mass something and then comes to rest inside the. Oh shit, that's 10 grams over there. Wait. Oh, not good. That's 10 grams. Not what we thought it would be. Okay. Oh, but then the mass of this, okay, that actually cancelled. Although it was in grams, the m factors cancelled out anyway. So, I mean, yeah, the mass on the right hand side was also in grams, so it works out somehow. Okay, 20 gram bullet pierces through a plate of mass something and then comes to rest inside a second plate of mass. Okay, two plates of mass. Then pierces the first one, comes to rest inside a second plate. What's the percentage? What? So this plus that's just 3 kgs. Okay, cool. The percentage loss in the initial velocity of the bullet when it is in between the plates is will let any loss. Oh, okay, that's it. Momentum conservation. Got it. So the whole system has how much of mass? It's just 4 kgs. So 4 times whatever new velocity you have, that's equal to 20 grams is just you know 0.02 is like 2 times of 10 power, yeah, 2.100, that just 2 or 1 upon 50. So it's just 1 upon 50 the mass, and then v squared, which we kind of don't know actually. Oh, sorry, just that of u, not u squared, it's just u. So v thing is just u upon 200. Wow, wow, really. Was this correct or what? Oh, okay. Velocity, initial velocity of the bullet when it is between the plates. Ah, that's what they're talking about. Okay, and the velocity loss, not the energy loss, of course. Okay, so you got the thing. You got what V is, which means the first thing or plate that moves with this guy is 2 energy conservation for that guy, right? Yeah, exactly. So the first is just 1 kg. So like u upon 200 is the momentum plus this momentum, which is, I know what this new velocity is. What is this new velocity? It's called as u dash. So the mass is 1 upon 50 u dash. Okay, that is equal to the initial momentum, which was just 1 upon 50 u. What does that mean? Just u upon 4 plus u dash is equal to u. So like u dash is equal to 3/4 u. So first it had u, now it's just 3/4 u. It's like 1/4 u is now gone. Yeah. So the loss in velocity is 25%. So please correct. Next question. Bullet of mass 20 kg hits a block of something suspended from massless string of length 100 centimeter and sticks to it. Mass is given. Here, this guy. Okay. From massless string. The bullet strikes the block at 30 degrees from the horizontal with the velocity of this thing. The block will rise through. Huh? Massless string of length 100 centimeter. And sticks to it. The bullet strikes the block at 30 degrees from the horizontal. It's getting weird. Okay. We lost it, this thing. So it's like it's it's striking at an angle. This is what's happening, right? Okay. The block will rise. First of all, it just has some vertical velocity. That's not good. Vertical velocity. That means that it will actually, this thing is not taut anymore. It will actually like do this parabolic motion until the string is taut once again, and then it will just, I don't know what it does. This is kind of not going good, isn't it? So what do you want? The block will rise through. Oh shit. You know what's the problem with this thing? Um, yeah, well, okay, can you just do energy conservation or something like that? I guess you can, right? It doesn't matter if it's taut or not in the end, because when it's at the highest point, your vertical velocity should be zero anyway. What about the horizontal velocity? It could be that your horizontal velocity is not zero. Then it just becomes complicated, doesn't it? Okay. Well, think about it. Doesn't matter what this parabolic motion initially was. In the end, the string just puts an impulsive tension and deals with the radial component velocity. So just get tangential component. Oh shit, that decreases its work. Oh no. Then you can't just do energy conservation, huh? Oh shit. So then this is actually the point where it has the maximum velocity. That's just not good. Oh, okay, that's not going good. Then if it is at okay, if it's actually larger than t upon 2, okay, this is not going good, right? You probably just have to do this thing, right? This is where it's going to be highest. Or if it actually like, if it becomes taut before this, then that's the highest point. Just too much of calculation, I believe. Lossless string sticks to it. This log. Right, this is just too much, isn't it? You will actually have to make cases and whatnot. This is not doing good. So what are the masses? It's just 1.98. This length is 100, like 0.1 meters. Okay. But I mean, like hopefully it won't be a big deal and like it can be taught very easily. We'll just see. We'll just see what the velocity is. So it's 30 degree from the horizontal velocity of 200. What's this final velocity going to be? Um, yeah, we just got 20 times. Oh, not 20. It's what? It is okay. 0.02. So okay, it's got 2 times of 2, which is 4. So 4 upon 2, which is 2. So 2 meter per second is the velocity. Just have 0.1 meter length string. This thing is 2 meter per second velocity. It's moving in this direction. Obviously, it's gonna like go in this way or something. We'll see if it actually reaches the highest point or not. Right? What's the length, by the way? It was just okay. Okay, whatever. So what's the highest point? And it's at what 30-degree angle, right? So it's a 30-degree angle, like this thing. So this is actually just 1 upwards, and this thing is sort of 3 in this way, of course. What's the time required? So the time period is 2u upon g is like 2 times of 1 upon 10. So 1 upon 5, but then you want half of that, just 1 upon. Hey, why am I doing this? Just want the highest part. Yeah, I want actually the whole thing, in fact. Yeah, the whole thing. So we're gonna use small t for this guy. Small t is, this is not good. This is just so stupid. Hopefully it's actually at a very high point. I have very less hope for this thing, but we'll see. We'll see what happens. Hey, what if it like it's, yeah, if it reaches at this point, then that's complicated, isn't it? So it just reaches before it reaches the maximum height, and then yeah, the tangential. Oh god, this could be that the tangential velocity is essentially in this direction, which would mean that it might even complete full. Yeah, it might even complete a full circle. Who knows? Your initial. Yeah, okay, this is not good. Definitely not good. Not a calculation you can deal with. Must have been something else to it. There's too many cases. Fine, let's see what happens. So that t value is just 0.1. So 0.1 seconds if it is the maximum height. What will that height will be? So r upon 2 value, the half range is just this time, the times of this guy is 0.1 squared. Okay, this is already going bad, isn't it? Yes, it's already going bad. If it was there, this would just be not good. Oof. Right. Okay. It's already, so as it goes up, and what's the height? You just figure that out. So you get half 80 squared, so half times 10 times t squared, just this guy's squared, just 1 upon 100. What do you get? 0.05. That's actually very small for some reason. Huh. Unexpected. But should this be happening? Why is it so small? 0.1 square root of 3. Wait, is that correct? Has to be. Right, it is just 0.1, and then the range upon 2 is just this guy again. Fine. The height is just half 80 square. Oh, it's just 1 upon 20, sorry. So 1 upon 20 is like 0.1 and then 0.05. Oh, that is what I wrote down. Huh. But then it's very small compared to this guy. Okay. So its height is not all that big. Its range is very big though. So it follows a shape like this. Okay, that's just too much. It's half of this, exactly half, right? Yeah, this is like 0.1, so whatever. So yes, it seems at some point this will actually just become taut and like this. Just have a look for where is that point. What if there is something else that could do? Hey, even if it actually does, no, you can't do energy conservation, unfortunately, because the impulsive force will, right? Yeah, I will just get rid of that extra energy that you have in the radial direction. So you can't do energy conservation anymore. Well, that sucks. Okay, so now what? You have to figure out when is this going to be taught once again. I'm giving up. This is just too much. Because first you'll have to figure out when is this going to be taught, then you will have to see whether or not this has enough energy to go full circle or yeah, yeah. Because it could be it just goes up and then it slacks down and then whatever happens. This is just so stupid, isn't it? Exactly. Like if it actually slacks, then that would mean that it does another parabolic motion and then that's the highest point. And this is stupid. Right. And moreover, you need to know what was that radial velocity that usually cancelled. Yeah, don't do this. This one is just not doable. Most likely they miswrote the question somehow and this ended up being this. Anyway, next. Weight of mass something traveling at speed of something tries to okay, just oh the same thing, huh? This is the same thing. Don't get it. So okay, the first one actually has 30 degrees. This one is what? Right, it just strikes, but in what direction? I believe it's horizontal because if it's vertical, everything's messed up. So, right, if it's any other direction than horizontal, everything would be definitely messed up. So now you can just do the usual energy conservation because the tension initially was right. I mean, there was no radial velocity initially, so you don't have impulsive tension throughout the motion. Okay, field of a grid after it emerges from. Are you serious? Okay, so like it passes through the block. Hmm, interesting. And you will just figure out what the velocity of this guy would be. It rises by how much? Vertical distance 0.1. So just have 2g h is equal to u squared. So g is just 10. Like 2 is equal to oh, just square root of 10. Square root of 10 is the velocity you have. Wait, that's not good. By this much height. So yeah, it's 2gh, right? So, but then that just means that huh, why do you even care about what the length of the string was? Is there something that I'm missing for some reason? I don't think so. I took care of the kinetic energy and we also took care of the fact that the impulsive force is not cancelling our energy. So it should really just work out. Right? Work distance is 0.1 meter, center of mass is block. So the block and bullet are different systems, right? Yeah. Right, it has to be just that. So 2g is equal to v. So the velocity of this guy is square root of 2 initially. So what do you have? Square root of 2 times this guy's mass, which is what is this guy's mass? 2 kg. So it's 2 times of square root of 2. Right. That upon the mass of this guy, this block. So it's 10 power into 2. So it's just a 10 power. 200 square root of 2 plus v, so the final velocity, which is equal to the initial velocity, which happens to be how much? 500. So our v thing is just 5 minus 2 square root of 2 times 100. Yeah, whatever. So what is this approximately? Just 5 minus plus of the 1.4 something, like 2.828, which let's do the proper way, just 500 minus this guy. 2, 8, 3. 3 is better. So just get 7. 9 becomes like 1. So 217 or something. Oh shit, 220. I'm gonna say it's B because 240 is too big for this thing. So probably B. Yeah. So 13 B. Next question. I think I got what they were going for with this question where it's like at 30 degree, just energy conservation and stuff, but definitely not the way that I thought this would be going. Okay, anyway, next. Hmm. We know that much. System of variable mass rocket propulsion. Okay, whatever. The mass of rocket is this thing, the relative velocity of the gas is ejecting from is just that with respect to the rocket. So, okay, the rate of burning of the fuel in order to give the rocket an initial acceleration of any, okay, the vertically upward direction will be. Just have dm upon dt something. You have to figure out what that is. So every time you emit a particle from the rocket, you have to give it some momentum to get it at this relative velocity. So where does that momentum come from? It comes from the particles like actually, it's like a pressure difference stuff going on inside, but I don't actually explain it. It's just like heated particles are hitting on the rocket and that makes them get that uh, momentum in that direction. Whatever. Yeah. So the thing is that that momentum that requires opposite momentum on the system. So that means that the rocket will actually have this thing. And by the way, there's another important thing I should tell you. Never use F equal to dp upon dt. All right. Never use that. Only use F equal to ma. This might sound contradictory to a lot of other people. What they say is that you can use F equal to dp upon dt and whatnot. Well, no, that causes a very big problem in our understanding because you won't know which forces are real and which are propulsion forces in that case. That's just a very bad problem to have. I had a problem and just I'm giving advice for that, right? Because I just won't want you to be confusing things because of that problem where you are using F equal to dp upon dt and then you don't know whether forces are real or not. Instead, when you use F equal to ma on a system that is not exactly a rigid body, that's okay. That's okay to do. Just have point particles in your system, right? Think of everything as a bunch of uh, point particles because if you don't, your system can have mass transfer and then your F equal to dp upon dt thing. It becomes a lot more complicated and unnecessary, and more importantly, it confuses you. So I would recommend don't use that. Anyway, so for this case, we're just using our system as actually we're not even using the system. We're just saying that Newton's third law says that momentum given to one body is momentum given from one body, and then like opposite momentum is momentum. You get the thing, right? Okay, so what that means is like every time you put up a momentum on these gas particles, you have to put opposite momentum on the rocket, right? So how much is that rate of the momentum on the rocket thing? Every second just every dt time just have dm mass leaking out of the thing of the rocket, then upon dt, and that times of the velocity at which is leaking out, not that, definitely not that. The thing is, it was already moving with the velocity that the rocket was moving with. Its momentum change is actually the change in its right. Its velocity change is actually its relative velocity because with respect to the rocket, initially it was zero, and now it's the relative velocity. So in the ground reference time, it was initially a rocket's velocity. Now it's rocket's velocity plus or minus depending on how it is the relative velocity. So it's really just dm upon dt times the relative velocity. So the relative, and that is equal to the force, the propulsion force on your rocket. Yeah. And what's that actually? Mass of rocket is this thing, electric velocity of the gas is this thing. The rate of burning of fuel to give the rocket initial acceleration, so they get the acceleration. So you actually know what the force is, just 20 times 500. So it's like the mass of the rocket times this guy's acceleration. Nice. Okay, let's just figure out what this thing is because that's what you're asking. So ma upon v relative. What is m? 500 kg. Are you serious? 5 times of 10 power 5 in that case. Okay, that is of acceleration is 20, just 20, and that upon the velocity relative, which is 250. Nice. So what do you get? Just get 10 upon whatever. Just 5 over there. So you just get 2 times of 10 power 5 upon 5 or something. And this is kgs per second. Yes, I think so. Wait, that's not making sense, but then it should. That's right, it's 250 over there. That's not 5 over there. 500. Oh shit, 500 kg. Sorry. This is not 10 power 5, it's just 5 times of 10 power 2, right? Okay. Kg is already assigned. I really thought grams was. Okay, just 500. So 20 upon. Yeah, for some reason I was thinking of this k as 1000. Whatever. Okay, upon relative velocity, which is 250. Or you can just say it's like it's 40 kg per second. That's not there for some reason. Wait a second, incorrectly or something. This acceleration over there is 250. Okay, it should just work out. Acceleration was 20. It's okay. Gas ejecting with respect to the rocket is 250, of course. Huh. Initial acceleration of this guy. Wait a second. Initial acceleration. That should be different than what I. Oh, okay, okay. So when it says this thing, what usually talking about is like acceleration after we factor in the gravitation. Yeah, okay, okay, okay. So the acceleration due to this force is actually just 30 in the upward direction, which means, yeah, it's 30 over there. So just 60 kg per second. So B is the answer. Next question. Next is check the following statements are true or false. The motion of rockets based on principle of conservation of linear momentum. Yes, it is. So it's true. Then the bomb, or you could, okay, whatever. You could also say it's like Newton's third law, but then whatever. When the bomb released from a cannon bursts into air, its momentum remains conserved, but the kinetic energy increases. Burst into the air. Momentum remains constant. I mean, yeah, okay. So it's momentum in. And this is kind of a weird thing, actually. Uh, wait a second. If you have this thing, summation of mi is equal to. Oh, it's gonna be complicated, isn't it? Okay, so summation of mi. So in at least in the xy and also actually yz direction because impulsive forces are not there. So summation of mi is equal to some kind of constant which is called like p, and summation of mi squared, half of that. Let's just say this is equal to 2 kinetic energy, right? And ui are just the velocities in a certain direction. Okay, then you can use the weighted what do we call it, the weighted power mean equality, of course, which means, which basically says that this thing upon summation of mi and the square root of this thing actually, well, this is actually bigger than or equal to summation of mi ui upon summation of mi, which is like p upon summation of mi. Yeah, just that. Which means that 2k upon summation of mi is okay. That cancels anyway. So 2k is bigger than or equal to p squared upon summation of mi. So you can just say this thing. So our kinetic energy is actually bigger than or equal to this guy. So when it splits, it's now a bunch of particles. Its momentum is the same, but now its kinetic energy could be bigger than or equal to this thing. Right. So yeah, I think it makes sense. It could be just bigger than that. But kinetic energy increases or remains same. That would be the correct condition, but whatever. Body can have potential energy without having linear momentum. Yes, it can. What's the big deal about it? In radioactive decay process, linear momentum can be conserved. You mean is conserved? Because yeah, it's not like can be, it is conserved. Momentum conservation principle can be applied to a system of variable mass if what is this summation of f external equal to 0. Yes, I think that's right. Wait. Did you just say variable mass? Okay, you can't just say that. It's like summation of f external equal to 0. It's kind of a complicated thing because you also have to take into account the like some forces are actually real and some are not real and stuff. And yeah, so for example, just take this simple system where you're having a solid brake or something. So it's a brake moving with a constant velocity v, and then we'll just consider this volume, right? So everything inside of this volume is our system, and as the brick enters or keeps entering into this, you are seeing that its momentum increases, like the system's momentum is increasing. But then what is the force on it? Like, where is the force? There is no force. There's no tension in this brick at all. So what's causing this force? The answer is propulsion. So yeah, you might not feel like it's propulsion, but it is because your mass is changing. So kind kind of complicated thing. That's why I never have systems where your mass is changing. So I don't know about E. I will not know at all because we don't know what F external actually means. Does this include a propulsion force or not? Probably not. Then this would be untrue. Okay. Center of mass of variable system. What is center of mass of variable system? A variable in what? Variable in mass or something like that? Always remains unaccelerated. I don't know what you mean by variable system. Just gonna move on. Gravity free space fraction of mass of rocket ejected out so that its speed becomes equal to the exhaust speed. Huh? It ejected out so that it becomes. Wait, what? Fraction of mass of the rocket ejected out so that its exhaust speed. Something's not right about this. Okay, the speed. So it should be 50% of mass that should be ejected out so that, yeah, and that should be doing it, right? The mass of the rocket ejected out. So it should be 50%, of course. You didn't say the mass of the fuel. Okay, the fuel could be the rocket itself, measured with that. It could be, right? But we don't know. So I think 50% is good enough, right? Emit your 50% mass, and then, yeah, like just moving with some velocity. It works out, I guess. This is kind of a weird thing. Was exhaust speed with respect to what? With respect to a rocket or with respect to the space frame? I don't know what they're talking about. A balloon has 2 grams air. A small hole is pierced into it. The air comes out with a relative velocity of something. If the balloon shrinks completely in 2.5 seconds, the average force acting on the balloon is. Is that velocity? There is a problem. There's atmosphere. So, yeah, I mean, like that could be causing forces on the system. Then how do you take that into account? Wait, can we just neglect that? We should probably not be neglecting that, but then fine. Just neglect air resistance and the force because of pressure differences in the atmosphere. I don't know. Just neglect all that stuff. And in that case, you can say that, okay, momentum conservation. So the force comes out. Okay, what air comes out is supposed to be 4 strings completely in 2.5 seconds, the average force on the balloon. So this guy's velocity is just 4. It has 2 grams air. So yeah, and the balloon itself has now what? Okay, the balloon actually doesn't have that much of mass, does it? It doesn't actually matter in any case because the momentum imparted in the exhaust is what we care about. So just 4 times of 2, or okay, 2 times of 10 power 3 grams. So just 8 times of 10 power 3 is the momentum in how much of time? 2.5 seconds. 5.2 if you will. So that just becomes whatever, 2.5. You know what? Okay, now just to write it a different way. 10 upon 4. That's more like it. 10 upon 4. 32 times 10 power 4. Yeah, that's the newtons. So 0.0032. Cool. Which is B. Next question. Uniform chain of mass m length L hangs on a thread and touches the surface of the table by its lower end. The force exerted by the table. Oh, this is like a famous question, isn't it? On the chain, when half of its length has fallen on the table, is assumed fallen part does not form a heap. Okay, whatever. Let's do this thing. So you have a chain falling down. Initially we're just touching it, touches the surface of, okay, by its lower end, the force is about the chain. Right, it's just like this, right? Exactly. So the xy velocity of this part is just zero, right? Yeah, exactly. Uh, there is gravity. It's definitely gravity. There's normal forces on this guy. Okay. Yeah. Well, we just need to think about what system should we take. Yeah. Wait, what is? Oh, and by the way, this actually relies on the assumption that this end has actually free fall going on, which is a weird assumption if you ask me. It's not completely obvious at the first, but it really is just that. What is actually happening is that this chain is sagging at the end, and that means that there's no tension in the chain. And since there's no tension, this part is just falling freely. Yeah, until it of course encounters this surface, and then it actually bends and becomes a part of this part, right? So what that means is like you can just figure out the velocity at any given moment. Okay, so they are saying when half of the chain is on the table. That means this guy has been displaced by L upon 2, right? So you can figure out the velocity of this complete thing. Actually, all of these points have been displaced by L upon 2. Just have what? Okay, actually, just do it properly. Energy conservation, no need for that, just kinetics. So V squared is equal to 2gh, right? So just 2g times L upon 2, which is just GL. So like it's just square root of GL, that's what this guy has its velocity. Okay, then its velocity is yeah, so like this guy, this dm mass, it just loses its velocity completely as it hits this part, right? This is actually in steady state anyway, so we're not talking about this. Its momentum is not changing. We are talking about this part actually, right? So this part loses its velocity completely and becomes a part of this thing. Now you might say, okay, this still has velocity, but it has velocity. It has no velocity in the z direction or in the height direction, which means you can just do what was I going to do? Wait, what was I going to do? Right. Just think about this complete system, right? Think about how it's changing its momentum. There is the normal force that's causing a change in momentum. There's also like pretty much no xy forces on this thing because there's no friction or whatever. Even if there was, it's just an xy force. So we don't care about that because we just want normal and gravity in what that direction. Yes. So what do you have? Normal force, right? And just like gravity, which is actually negative. And we'll think about where is the momentum changing? Is momentum is okay? We will see. We'll see what's going on. This is still very weird. So minus mg, that's equal to. So first of all, here's what I talked about, that this dm is just losing its velocity. So that causes, wait, this velocity which is negative, right? So it loses a negative velocity, it's like positive, right? Yeah, it gains velocity in this direction if you want. Wait, is this freezing? Okay, whatever. So the velocity that gained is how much? This dm times v, that's the momentum it gained, and that happens in time dt. But then dm upon dt is just the mass density, or you could just say m upon l, that times of the velocity. So like just v squared over there. But we only know that v squared is just gh. So this will just be like mgh upon l. Oh, sorry, gl upon l. Okay, just mg. So this is just mg for. Wait, is this it? There's also the acceleration because of. Oh shit! What happened? Wait, why did this happen? Okay, just wait a second. I think I should really change my setup because this happens a lot of times. Anyway, what I was saying is that that's not it. You also have another thing going on. You have this part accelerating. Yeah. And what is this guy's acceleration? Is g, of course. And it's in negative direction. And yeah, just negative of this guy's mass is in this case what? Just m upon 2. So negative m upon 2g. Yeah, that should be the thing. So what we just have is the normal force is equal to. Wait, that was the thing, right? Just sorry, it's m upon 2g. That's, oh, it's also just m upon No, it is just mg because there's also this guy, of course. Yes. So the normal force is just 3 upon 2 mg. Wait, right? Yes, okay, that was the actually, that was the thing, of course. It's just three times of the, yeah, three times of the mass lying on the floor, that types of gravity, right? That's what the normal force is always going to be. You can just prove that. So I just showed you what it's like for a special case. You can prove it for a general case. It will just be three times um, of the force exerted on the fallen part, right? That's what the actual normal force will be on this complete system. Okay, cool. So that's what we want, right? The table on the chain. So just 3 upon 2 mg. So B is correct. Okay, and it's like collision, which uh, okay, I guess we should stop for now. So I'll see you in the next video.